Okay, physics geniuses, this is the magnetics lab. I'm sorry it's taking me so long to post this. I'm finally getting to it. We were supposed to do this yesterday, which was Tuesday, the 14th of April, but I'm doing it instead on the 15th of April, figuring that you were going to study for your exam anyway. So anyhow, the handout is on Moodle. And what you have to do is you have this handout here, which is the magnets tutorial, and then you also have to fill out the magnets homework. So both of those will be due by the final exam next Monday. Okay, so on Monday, these both will be due. What I'm going to do today is I'm going to walk you through the magnets tutorial. Okay, and first of all, we have magnetic objects, or we have objects that have the potential of being magnetic. All you can see is my hands. I don't know why I'm doing that there, but so we have an iron rod, we have a brass screw, we have a copper penny, we have a wooden dowel, we have an aluminum dowel, and we have a plastic dowel. Okay, and then we have magnets. Okay, and we're going to play with these and sort of classify them in different ways. So we know that our first class of objects are permanent magnets. These are things that have magnetic poles that will attract other things that have magnetic properties. Okay, so if I take my permanent magnet and I try to attach plastic to it, it doesn't attach. Okay, it's just gonna fall off. It just falls onto the bench. Okay, so that would be class 3, things that are not attracted to magnets at all and not magnetic at all. Okay. Now I have my aluminum rod. Same thing happens. No attraction. Okay. So that would be class 3. Now I have my iron rod. You'll notice it is attracted. Okay. It is attracted, but it isn't necessarily a magnet. So we put that in class 2. They are objects that are attracted to magnets, but aren't magnetic themselves. So class 2. And then finally, then I have wood, obviously not attracted to a magnet, so that's class 3. I have brass. Brass does not attract to a magnet, so that's class 3. Then I have copper. Copper is not attracted to a magnet. Usually you have to have some type of iron component associated with it, although there are other magnetic metals. So that's also in class 3. So if we look at our 3 different classes here, we have classes 1, 2, and 3. I'm going to push that back a little bit so you can see it. So I have class 1 as magnets, class 2 as objects that are attracted to magnets but not magnetic themselves. In class 3, objects that are not magnetic attractable, so there's no interactions. So a class 1 object would relate to itself because it would take a magnet, then that will attract another magnet. So in terms of your table, filling out the table below, 2 magnets will attract. 2 magnets will also repel. I can't pull these together, so these are going to repel. Okay. So for class 1 and class 2, the magnet is attracted to class 2 from either pole. It is attracted to class 2. And then between class 1 and class 3, there is no attraction. I can just wave this around forever and nothing's going to happen. Okay, between class 2 and class 2, nothing's going to happen. I could take this iron rod and I could put another iron rod up to it and nothing would happen. Between class 2 and class 3, nothing happens. And then with class 3 and class 3, these don't interact whatsoever. There is no type of magnetic force there. Okay, So in number 3, are all metals in the same class? No, obviously not. We have copper that's in class 3, we have aluminum that's in class 3, and then we have iron that's in class 2. Okay. Okay, now the next exercise is to take a permanent magnet and something that is magnet attractable and see if you can determine which one is the permanent magnet. Okay, so if I take a permanent magnet and I place it anywhere along these two areas, then the magnet is going to attract more likely to the poles, okay? Now, if I take the non-magnetic but magnetic attractable object and I move it to the center, there is no attraction between this area and this area, whereas if I do this and move this one to the center, then there is attraction, okay? So a magnet at the middle between the north and the south poles has no attractive properties, okay? But if I move this to the other end, then it is attractive and it will stick anywhere on the metal that is magnet attractable but not a magnet. Okay, so magnets, if you're in between the two poles, there is no magnetic force there. Okay, so there is no magnetic attraction. However, non-magnets, it doesn't matter where it is, it's going to attract directly to a magnet. Wherever you place it, it will just attract to the magnet. Okay, so magnets have poles. Objects that are attractable to magnets do not have poles. Okay. So the magnetic poles, we determined that this has two poles. We call this the north and the south pole. Okay. And if I take two magnets, I'll find that sometimes the poles repel and sometimes the poles attract. Okay, so if I have opposite poles, they will attract, but if I have similar poles, then they will repel. These don't come together. Okay. Likewise, if I flip, then the same poles attract or repel. But if I flip again, then they'll attract. Okay. So depending on how I line up my magnets, then they'll come together, or I can't force them together. They'll fly apart unless I can get them to interact with their poles. Okay, so that shows you that we have two poles on a magnet and certain poles attract and certain poles repel. Okay, so if I line these two magnets up, put them in distances far enough away, then I can distinguish one type of magnet. If I take a third magnet, I can distinguish one type of pole that's on this end here. I get repulsion. Okay, and on this other end, okay, or if I put them together like this, these both repel. Okay, or if I go to the other side, then they attract. Okay, if I go to the other side and I flip my magnets, then these will repel. They repel. Or if I flip them again, then they will attract. So you know you have two unique types of poles, and you can distinguish one pole from another just by taking a magnet, your third magnet, and then seeing which sides attract and which sides repel. Okay, for the next experiment, I'm going to skip part D. I'm having trouble with the uncharged pith ball, but essentially what happens is with an uncharged pith ball, usually if you had something with charge associated with it, it would attract. But with a magnet, it neither attracts or repels. Okay, so there is no net charge on the north or south pole of a magnet, but you can skip part D. But I've got part E. I've got a paper clip here, and it's suspended from a string. I'll try to get this in the frame just as best possible. Okay. Now, if I have a source of charge like a battery, and I put this paper clip in a foil-lined cup, and even if I bring the battery near, it's kind of difficult to see down in the cup, so I'm going to have to describe what's going on. But even if I bring the battery near to the cup, there's no interaction between the battery and the cup. The reason why the foil-lined cup creates an electric field inside the foil that is equal to 0. Okay, so there's no net interaction with the charge. Okay, however, if I take my foil-lined cup out, and then I try to interact the battery directly with the paper clip, work with me, it will stick. It sticks, okay? But it gets overcome by the force of gravity after a while, but there's enough of a charge separation on the paper clip that it's going to stick to the positive terminal of the battery. So with a foil-lined cup, it doesn't happen because the electric field is nullified as soon as I get inside that foil. Now, with a magnet, you would expect that a paper clip being made out of iron, it would attract to a magnet right away, and it does. Very strongly attracts to the magnet right away. Okay, but if I put it in the cup, and I'll describe this, you can't see it, then the aluminum foil does absolutely nothing. It's still, you can hear it hit. I'll do it again. So the aluminum foil does nothing to stop the magnetic field. So the magnet is attracted to the object regardless of whether you've got metal shielding or not. So based on this, then the magnet is attracted to the paper clip even when the paper clip is inside the cup. So we know that we're dealing with different forces than electricity. Magnetism is distinct than electricity because we can't shield magnetism with some type of object or some type of metal object like tinfoil. Okay, now we're gonna have fun with a compass. Okay, so we have a compass and a magnet, and normally without the influence of a magnet, I'll put it over here, then this will align so we can see directions of north and south. I'm holding it up, so it's a little bit difficult to see that, but you can see that it aligns towards directions north and south. And if I put it towards me, then it says north is about over there, which is correct, towards the Mount Shasta, and south is down towards Sacramento. Okay, however, if I take this compass and I put it in relationship to the magnet, I can make the compass do all sorts of nifty things. Okay, so if I take my compass and I have the North Pole attracted, and I hold the pole of my magnet to the pole of my compass, then the South Pole of my magnet is going to align with the North Pole of my compass. Okay. Now, if I switch it around so I'm not in between any pole, then the North Pole is still going to head towards the South Pole, And the South Pole now, the white part of the compass is going to head towards the North Pole. I keep on twisting around, and I get to the North Pole of my magnet, and it's attracted to the South Pole of my compass. Okay, so I can change the behavior of my compass, which is magnetic, and it's not only magnetic, it's magnetic attractable, but it is class 1 truly magnetic object. Okay, and I can change the orientation of my compass because it is also a magnet in the same way that I can change the orientation of my magnet itself. Now, if I put this all alone, okay, out of the influence of other magnets, then you can see that it will ultimately land on a spot and orient. And that is because the Earth is one big magnet. So when this compass points towards the Earth's north magnetic pole, it points towards the Arctic, it's actually pointing towards the south pole of the Earth. Okay, so we refer to that as the north magnetic pole, but it's actually a south pole. Okay, and then the other end is oriented down towards Sacramento, and we call that the south pole of the magnet. But if we go down to the other side of the Earth, down in Antarctica, then that's actually the north magnetic pole of the Earth. So if I take my bar magnet, and here's my North Pole is here. You can see that. North Pole is here and South Pole is here. Then I can take my magnet and I can put it at different locations. I'll put it at location A. And I don't know if you can see that very well, but you can see the deflection of the needle there is away. Okay, and up at an angle. Here, if I put it at point B, then the North Pole points directly away from the North Pole of the magnet. If I put it at point C, it's a little more difficult to see, but you can see that it's pointing diagonally away from the magnet. If I put it at point D, and then if I put it at point E, then at point E, it's flipped around, so the North Pole of the compass is actually pointed towards the South Pole of the magnet. Okay. Now, and you'll notice that with my magnet, the further I am away from my magnet, the more the compass needle tends to oscillate. But if I move it close, then the oscillations become less. Okay, so the magnetic field is becoming stronger as I get closer and closer to the magnet. Okay, and it moves into position very, very quickly. However, it takes a longer time to move into position if I'm further away from the bar magnet itself. Okay, so the direction of the magnetic field corresponds to the direction that the needle is pointing. So it's pointing from north to south. So we'll go from north to south, those lines will move. And so you can draw magnetic field vectors all around the magnet, going from north to south to north, and vice versa. Now, if I have a segmented magnet, you'll notice that this is in segments. Then if I put them all together, then the North Pole is still the north and the South Pole is still the south. So it will behave in the same way as my bar magnet, even though it's in segments. Okay, so it behaves in the same way. But if I break it into segments, then that will create a new North Pole and a new South Pole each time I break it apart. So I get the same response regardless of whether I break the magnet into segments. Each time it establishes a new North Pole and a new South Pole. And obviously, the more segments that I have, the stronger the magnet it is. But every time I break it into smaller numbers of segments, then I still get a North Pole and a South Pole, regardless of how big the magnet overall is. Okay, so even if I took this bar magnet here, where's my bar magnet? Oh my goodness, oh here. Okay, so even if I took my bar magnet here and I broke it in half, I would still get a North Pole and a South Pole for each segment. So even if I do something more complex, where I have two of my segmented magnets, then I can use the principle of superposition in order to know that my compass, I have to move these closer together, is still going to point towards the South Pole of the magnet. Okay, and it will orient, it will superimpose these two magnets here, and it will orient then over here away from the North Pole of the magnet. Okay, and if I'm somewhere in between these two magnets like this, then the North Pole is going to point to the South Pole of the magnet. The South Pole of the compass is going to point to the North Pole of the other magnet. Okay, so the two magnetic fields are interacting, and they're actually additive, so you can use superposition in order to predict the strength of the overall magnetic field from these two magnets. So I move further and further away. Then I start to get influence of the magnetic fields going away. And then this reorients as if I am in between a bar magnet, and this is just one big long magnet. Okay. So for page 117, then you should be able to look at those questions. And you'll notice that when I'm outside of the magnets, then my needle just kind of meanders around. However, if I'm directly in between these two magnets, the needle snaps into position. So that tells you that in between the two magnets, directly in between, the strength of the magnetic field is much stronger than if I am further and further away from these two magnets. Okay, let's do the next experiment. So I'm on page 119. It says EM 119. And so I have an apparatus. Don't know if you can see this, but I've got a wire that's carrying current going from red to black. Okay, and then a portion of this wire, I've got this green loop down here. Okay, and so in the green loop, I've got current going through the wire. I've hooked it up to two 1.5 volt batteries, so it's a total of 3 volts. And you'll notice that this interacts directly with the poles of the magnet. So if I look at the south pole of the magnet, when I put it up to this current carrying wire, not sure if you can see this or not, then I get a slight attractive force. So you see the wire is just moving very slightly. Okay. So actually that looks like more like a repulsive force. It's hard to get these two to touch. Okay, now if I switch the leads of the battery, so the current is going in the opposite direction, and I use the same magnetic pole, then I get an attractive force. Okay, so that's part B. Now I turn over the page, and I hold the north pole with the battery unconnected. Okay, so the battery's not connected, so I hold the north pole. And there's no force whatsoever. There's no current, so there's no magnetic interactions there unless there's current. Sorry, I was off the screen. Okay. If I have the battery connected, the closer that I get to the current carrying wire with my magnet, the more interaction that I see. Okay. However, if I go parallel, you get some interaction there with the current just because the wire is bending. But if I go parallel with my magnet, so north poles and south poles are lined up with the current, then I get absolutely no interaction. So when they're perpendicular, okay, when I have a perpendicular force, then I get interaction. But when I have a parallel force, then there's no interaction. So these magnetic fields are working at 90-degree angles from each other. Okay, and it turns out the force is equal to the current times the length of the wire times the cross product of the magnetic field. So cross product, that would be sine of theta. And so when theta is 90 degrees, I get a stronger force. When theta is 0, then I get no force. Now, if I take my wire and take my compass, then I'll actually see I'm going to move my other magnets. Okay, far away from my wire, my compass gets into equilibrium, but as soon as I get closer and closer and closer to the wire, then it's subject to, I don't know if you can see that very well, then it starts to point directly to the wire itself. Now, if I change the polarity, okay, remember the north pole was pointing towards the current carrying wire. But if I change polarity, then that changes the direction of the magnetic field. And now it makes the north pole actually bend a little bit and go away from the current carrying wire. It's difficult to see there, I do apologize. So it's bending a little bit away due to the strength of the magnetic field relative to the Earth's magnetic field. This current carrying wire is not producing much of a magnetic field, but it is producing enough magnetic field that it would overcome the Earth's magnetic field. And you can, for part C on page 21, you can see different configurations depending on the current carrying wire. And you can actually sketch the magnetic field lines of the current carrying wire. So depending on this orientation here, then you can sketch the magnetic field lines around the current carrying wire. I think what I'll do is I will, where it says current loops and solenoids, you can stop right there, okay? So up to the first two, part C and D on page 121, do that. Then the rest of that, this is getting overly long. And so, and difficult to do with not being in person. I'm just going to go ahead and curtail the lab at that point in time. So you'll be responsible for the handout from page 113 to page 121. And then also the magnets homework handout. And then on page 114, you get to the 13. Okay, and that concludes this video laboratory. Thank you for your patience.